our previous lessons, we have learned about the systems and transformations. So we saw that if you have an input x of n, for example, and then you pass it through a system, then there would be some transformation. And this transformation would give you a new output, y of n. And we saw that the transformation can take different forms. For example, if I have y n of n equal to xn plus xn minus 1, then we are simply saying that when the system gets the output, when the system gets the input x of n, then it adds it to its delayed version x of n minus 1 to get the output. In fact, if I were to draw this, then I would say that you have an input x of n, and this input x of n, you need to pass it through a delay, a unit delay, and then you sum it up, the delayed version, with the part which is not delayed, x of n minus 1, to obtain the output y of n. So how exactly do we implement the delay? So we saw in the lessons of Z transform that if I obtain the Z transform of this function, then I will have y of z equal to x of z plus x of z minus 1. So in the z domain, a delay is represented by z raised to minus 1. So that if I were to replace this delay by its equivalent in the z domain, then I would have z raised to minus 1. So I would say that an implementation of this system would be in this form, where I have x of n. Then I have a delayed version, z minus 1, so that here I can get xn minus 1. Then here I have a summation of the two, x of n and x of n minus 1, so that I have x of n plus x of n minus 1, this being y of n. So you can see, if you look at these implementations that we're looking at here, that some of the elements that you need would be a delay element. You need a delay element to implement the system. You also need a summer. But you may also need a multiplier. For example, if the system we have given up there, y of n equal to x of n plus xn minus 1, let's say this was multiplied by 2, and this is multiplied by 3. Then you need to have the coefficients so that I have my x of n as the input. Then a delay is z minus 1. Then whatever I have here, I may need to multiply it by 3. I have a 3 there. which indicates the multiplication. And no, actually it's via 2. So you have a 2 which indicates multiplication, and here I have 3. Then I can have my summer. Then I have this input. Then I have my y of n. So I shall also use the multiplier. And you can already be able to imagine how exactly we can implement this in a computer program, for example, that you only need to have the delays. Once you have the delays, the input comes, there would be delayed and scaled version of it. Because here, if you look at this, this is not delayed, but scaled. This is delayed by 1 unit and scaled by 2. So the type of operation that we can have on the signal can be performed here, then we get the output. Remember, we had discussed different types of signal operation that can be performed on the signal. And when we do this, when we delay the signal and when we delay, scale it, what would happen is that the output which is received would in a way be related to what the inputs were, but they may be different in frequency, in amplitude, in phase. Or basically we are saying that there would be some filtering which shall have taken place. There would be some filtering, or simply varying the characteristics, of the input signal based on some rules. To obtain the output. So we vary the characteristics of the input signal based on some rules to obtain the output. Of course, based on some rules to achieve a certain objective. But it may also happen that the natural systems, like free space, say you have a free space, and then you are to pass some signal through free space, then it will still be affected by the free space, so that we get the output y of n. And instead, we may be interested in getting to know exactly how the free space affects the signal. So how does the free space affect the signal? Or how is the signal affected when it passes through the free space? So it may happen that we don't have the characteristics of this one, but we may actually derive the characteristics and find the filter characteristics. So we have two main types of filters when we talk about the filters, and I can illustrate this by giving two examples. Let's say I have y of n equal to x of n plus x n minus 1, like the previous example I had given earlier. If we were to get the z transform on both sides, then I would have y of z equal to x of z plus x of z, then z raised to the minus 1. Where I have x of z into 1 plus z minus 1 equal to y of z. What the transfer function would be y of z over x of z equal to 1 plus z minus 1. Or if I denote this by h of z, if I denote this by h of z, then I will have h of z equal to 1 plus z minus 1. Let's compare it with this is my first function. So let's compare it with the second function so that I have y of n equal to x of n plus xn minus 1 plus yn minus 2. Let's see if we get the transfer function of this. The z transform, I would have y of z equal to x of z plus x of z, z minus 1 plus y of z, z minus 2. Then I can collect the like terms together. So I will have y of z minus y of z, z minus 2 equal to x of z plus x of z, z minus 1, or y of z into 1 minus z minus 2 equal to x of z into 1 plus z minus 1. Then I have y of z by x of z equal to 1 plus z minus 1 or 1 minus z minus 1. And this gives me h of z equal to 1 plus z minus 1 over 1 minus z minus 1. Okay, so let's compare the two equations. What we have here, what I have h of z, the first one I had this, h of z equal to 1 plus z minus 1. There, let me call it h1 of z, so that I have h2 of z equal to 1 plus z minus 1 over 1 minus z minus 1. And let's also have their corresponding time domain expressions, which we have seen that in the first case, y of n equal to x of n plus x of n minus 1. And here, y of n equal to x of n plus x n minus 1 plus y n minus 2. So in the second case, you can see this is the output, but this part of the output that we are feeding to the input. Or we can say we have a feedback loop that feeds part of the input, that will be part of the output to the input. But in this, there's no part of the output which is fed at the input. If I were to illustrate this, you can see that I will have my x of n there. Then that x of n is a delayed version of x of n by 1 unit, z minus 1. I have x of n. Then you can see I have I will have y of n. I will have, if I add here, I will get y of n, x of n, xn minus 1. But we need to bring this part. So it means I have to get the output delayed by 2 units. 1 unit there, maybe I delete on that. I delete by another unit, z minus 1. Then we make it to be part of the input. I can have it like this so that I have here actually I can have my y of n here now, because we have taken this one that we have here. We have the y of n here, delay it by 2 units, bring it, add it to this. Because you can see that if you check now what we have here, I have x of n plus xn plus 1 plus this, which is delayed twice, yn minus 2. So here, we will say that here there is a feedback. That means that if, for example, you put the input so that we have x of n, and after that, you do away with the input so that the input is no longer there, this system will continue having a value, because whatever the output was, the system will continue feeding it back to get the output. Or we can look at it like this, because we have seen that systems are defined by the impulse response. So systems are defined by the impulse response. So in one case, where we don't have a feedback, where there's no feedback, the impulse response would actually be finite. That is, if it has a finite impulse input, then the output will also not be continuous. The output would be finite. So we talk of finite impulse response filters, where we don't have a feedback. And you can see that if we don't have a feedback, we are also not going to have poles in the transfer function, because we don't have the denominator. We don't have the denominator, we don't have poles. So what we call the finite impulse response filters, no feedback. In their transfer function, no poles. So they are always stable. The response cannot be, is not infinite. But the case where we have the infinite response is where you have a feedback. It means if we feed it with an impulse signal, then the output would be infinite. Because the moment we have an output and then it is continually fed at the input, then there's no end to it. We talk of infinite impulse response filters. So in the infinite impulse response filters, this feedback, you have a feedback or the input or the output to the input. And of course, if we get the transfer function, then we would also find that it has poles. It can be unstable. Also, what you mean by unstable, you find it has a finite input, but the output is infinite because part of it is being fed back to the input, so that even if you are no longer applying an input, then the output would always be there. So we can actually have a formal expression of such type of filters, so that when you have the one that you call the finite impulse response filter, then it means the output y of n is simply made up of the input or scale versions of the input. Let's say from k equal to 0 to m, p of k, xn minus k. So we have delayed scale versions of the input. And you can see, for example, if we take k to equal to 3, then we'll be saying that y of n will be given by k equal to 0 to 3, p of k, xn minus k. Which would be b naught x of n plus b1 x n minus 1 plus b2 xn minus 2. So long as n lies between 0 and m, then the outputs would be defined by the coefficients of this. Okay, so now we have y of n is equal to this expression. But we have seen that if it is a finite, it is infinite impulse response, then we would have the output y of n being given by that part of the x, part of the input, but there would also be the part which is fed back, maybe k equal to 1 to n, ak into yn minus k. Okay, because we have this part of the output which is fed back to the signal. So in any of these filters, like this one, if we have these coefficients, then it fully defines what the filter does. The coefficients B0, B1, B3. Because what that one would imply when we are implementing the system is that you just have your input x of n coming, the one which is not delayed multiplied by B0, the one which is delayed by 1 unit multiplied by B1, the one which is delayed by 2 units multiplied by B2. So if this is implemented in a computer program, then we only need to store the coefficients B0, B1, B2. Then when the signal x of n comes, then the multiplied by this, but a delayed version by 1 unit multiplied by this, and a delayed version by 2 units, multiply by this, then you get the output. So that is what the system will be doing. So the coefficients B0, B1, B2 are very important. And you can see that if they are few, then the complexity of the system is also reduced. If there are so many, then you would actually have a bigger program, more time of execution and the rest. And for the for the infinite impulse response, infinite impulse response filter, you can see there are two sets of coefficients. The coefficients which are meant to multiply the input x of n, and the coefficients which are meant to multiply the output, the delayed versions, the delayed and scaled versions of the output, AK. So here you need a set of two coefficients. You need the PKs, and you also need the AKs. So if, let's say, we have a filtering function to be performed, if we have a filtering function to be performed, then this can be realized by either using IIR filter or FIR filter. So either of them will do the filtering, but there will be difference in terms of implementation, in terms of the coefficients required. It will be found that if you use an FIR, then you need many coefficients because they are just one set of coefficients in the numerator. So you don't have a denominator here. But here they may be slightly fewer because you have two sets. You have the BK and the AKs to play around with to achieve the same function. So that is one of the differences that may result when we are actually implementing using either of these filters. But also there are some other key differences which differentiates this type of filters or when we are likely to use the filters. So let's look at some few examples of the differences between these filters: finite impulse filter and infinite impulse response filter. So for the FIR filter, first of all, you don't need to start from the analog filter. IIR, you need to start from the start the design of the filter from the analog versions. Like Chebyshev filter. So we can see some advantage of that because very good methods have been developed for designing the analog filters. So the moment you can design an analog filter, you can get the digital counterpart. But for this, we don't need to start from anywhere. We only need to start from the problem. What is the problem which needs to be solved? And therefore, it is easy to design an FIR filter to solve a given problem. So we can talk of optimization based design. We start from where the problem is and we design our filter based on the problem which is there. This one also is mainly used to block or allow certain frequencies to pass through the system. So we can talk of frequency selective gain. Frequency selective gain means it is mainly used to choose which frequencies will pass through the filter. But this is more flexible because we can talk of arbitrary magnitude response. So if it's arbitrary magnitude response, then what it means that you are able to design it based on any criteria, that is, as long as the criteria is well defined. Then we'll later see something about the phase, the significance for the phase of the circuit, initially when we apply it to the filters. So this one is having non-linear phase response, which is actually a disadvantage. You don't have no control over the phase. But this one is having linear phase response. This results in less distortion. And because of the coefficient that you are talked about, this one needs fewer coefficients. Because you have two sets of coefficients to play around with the n and the an. So this requires a larger n. So these filters have different types, ways of designing them, and whichever is to be designed depends on the problem which needs to be solved. And the realizations also depend how we realize each of these filters. It actually vary. So let's look at different forms of realization of the filters. Okay, so I've explained that when we are realizing the filters, we actually need multipliers. You need adders. You need delay elements. Which may be in form of flip-flops. Then you'll be able to realize the filters. And in realizing the filters, the common methods or common forms of filters are that we have what we call the direct form 1. We have what we call the direct form 2. And we have what we call the cascade implementation. Then we have parallel implementation. So let me start by giving an example of direct form realization. So I will illustrate this by using an example. So let's say I have y of n equal to 0.5 into yn minus 1 minus 0.25 yn minus 2 plus x of n. Plus x of n plus 0.4 x n minus 1. So this is this one that we want to realize. You can see that this is an IIR filter because we have parts of the output which is fed back. We have the part delayed by 1 unit, part delayed by 2 units. So what we need to do, have another variable, just separate them. Separate the inputs. So I can write this one as let x of n plus 0.4 x of n. Let's separate the x of n ones equal to omega of n. Then I can have, can rewrite the equation y of n equal to 0.5 y n minus 1 minus 0.25 yn minus 2 plus omega n. So this is what we need to do. Then at this stage, we can implement this first part so that we get this output here. So you have the input coming, x of n. We need a delayed version of it. So since I have x of n, you need a delayed version of it. Z plus 1, you say this equal to unit delay. So that here we have x n minus 1. Then bring it here, add it. So this one comes here, this one comes here. So here you get x of n here. Here you get x of n plus x n minus 1, which is our omega n there. Then the other part, you can see in this, omega n is just part of it. So you'll have this, like having 2 parts of it. y of n have you have a delay, a maximum of 2 delays, 1 delay, 2 delay. So I will draw, this gives me 1 delay, z minus 1. Second delay, z minus 2. And so that here I can have yn minus 1. Here I can have yn minus 2. Then I will have, I can add this. I need this and this. But yeah, what we also didn't do, we needed to put a 0.4 here to multiply xn minus 2. Yeah, I also need to bring this here, multiply by 0.5, this one here. And this other one multiply with minus 0.25. So we add it to this, bring it there, then bring this, add them, so that we get y of n. So the arrows in the branches indicating the direction of the signal flow. So this is the implementation. So you can access how economical this implementation is. I may be counting the number of delays used in the circuit. If I have, let's say, the delays which have been used in the circuit, delays. This one here is 2, is 3. 3 delays. How many multiplications do you need? 1, 1. Even this one is a multiplication. You can say it is multiplied by 1. Though we may leave this out, but it is the same as not multiplying also. So we have 1, 2, 3 multiplies. We have 3 and 3 additions. 1, 2, 3 additions. Also 3. So this gives us an idea about what you need to realize to what is it that you have to forego to use to realize this system. So this system we can realize using the hardware. Can realize using the software. Now add what is called the software defined radios, where everything is in software. We can process all our software, our filters in software, everything in software. So this would be an acceptable implementation. So now you are able to realize a signal using the direct from 1. You can try this. We'll try this. Okay, so try this. Try running this using the direct from 1. So the other method I talked about was the direct form 2. Direct form 2. So I will also illustrate this by the procedure by going through an example. I have y of n equal to minus 0.1 y n minus 1 plus 0.72 y n minus 2 plus 0.7 x of n minus 0.25 z to x n minus 2. So the first procedure here is to obtain the z transform, something which we didn't do in the direct form 1. So obtain the z transform. But this one you can easily, for most of the functions, you can easily write this one down without referring to any table. Because I have here, starting on this side, yz equal to minus 0.1 z minus 1 plus 0.7 2 yz z minus 2 plus 0.7 xz minus 0.25 252 is 2 actually. 252 z is equal to x or z. Then collect the like terms together. And if you do that, we'll have y of z into 1 plus 0.1 z minus 1 minus 0.72 z minus 1 is equal to x of z into 0.7 0.252 z, or we have yz over x of z equal to 0.7 minus 0.252 z minus 2 over 1 plus 0.1 z minus 1 minus 0.72 z minus 2. So this means that if this filter function was written in the z domain, then we'll start our implementation from this point. Just the same way that we introduced the variable omega x, omega of n, omega of n, we'll also introduce another variable, wx. So bring another variable. So that we have y z over w of z equal into w of z over x of z. This still gives us the same value as y of z or x of z. As you can see, this would actually cancel and would remain with this part. So once you have written them like that, then we would associate y of z over w of z, associate with the numerator 0.7 the 0.252 z minus 1. And the remaining part, this part, that is w of z over x of z associated with the numerator. Not the denominator, but because that when you multiply them, you still get this fraction. So we'll have 1 over this. So 1 over 0.1 z minus 1. 0.72 z minus 2. And you can see here from this, because this one equation 1, or this one equation 2. So from equation 1, I have y of z equal to, just cross multiply 0.7 minus 0.252 z minus 2 into wz. And I can expand this. If I expand this, I will have y of z equal to w will have 0.7 wz minus 0.252 z minus 2 wz. And in the time domain, I want to come back to the time domain. We'll have y of n to 0.7 wn minus 0.252 yn minus wn minus 2. Okay, so I'll call this 3. I'll call that one 3, and then I'll come to this, do the same, follow the same procedure. Because I will also have, if I cross multiply, we'll have wz into that, wz into everything here. Some cross multiplying, so I have, I'm doing this cross multiplication, this, so wz into 0.1. Actually, I can write down everything in one step. So it's hard for that multiplication. I can have wz into plus 0.1 z minus 1 wz minus 0.72 z minus 2 wz equal to x of z. And in the time domain, I will have wn equal to x of n minus 0.1 omega n minus 1 plus 0.72 omega n minus 2. So this one 4. So the equation that I want to implement, this one's in the time domain. I will bring them together so that I have y of n, just write down here, y of n equal to 0.7 w of n minus 0.252 w of n minus 2. And w of n equal to x of n minus 0.1 w n minus 1 plus 0.72 w n minus 2. So in terms of implementation, let's look at this carefully. I have my x of n as the input. Then this x of n, you can see the, let's see, how do I obtain x of n? I have in other words, what do you need to implement x of n? You need to implement x of n, you need wn minus 1, wn minus 2, and actually wn. So I can have the intermediate variable I have is wn. So I need wn minus 1, so I have z minus 1, wn minus 2, so I have z minus 2 here. Because here we'll be able to get here wn minus 1. At the end of this, I will be able to get here wn minus 2. Then you can see I need to add wn minus 1, wn minus 2, add them, bring them here. But of course you can see, yeah, bring them there, add them. We have them here. On this one here. Then now, once I have that, I have the xn. I can bring the xn there. So you can see my wn here. I have the xn coming in there. I'm adding the negative wn minus 1 and multiply by this negative 1 to get this. By this also 0.72. So this, you can see that this one I've actually realized this wn of n by bringing this and the delayed versions. So I shall realize this part. Then you can see this other part, y of n. I only need delayed version. I also need wn, which is already here, and a delayed version of wn minus 2. Delayed version of wn minus 2. So bring that one. Then I add them there. Then I will get y of n. So you can see now we are able to share some blocks. The two delays are here. We are sharing this side and this side. So this is likely to be more economical. Because now the delays here are better like this. In this system, I have two delays. I have 1, 2, 3, 3 others. Well, if you look at the previous one, no, they are not identical, but you can see the way the delays are spread all over. So this makes direct tool form more efficient in terms of the number of gates which are used. Okay, so in this lesson, we have actually defined the types of filters. And then we have looked at the direct form 2, 1 implementation, and direct form 2 implementation. So in the next video, we'll look at the other forms of implementations.